Hello everyone. So we continue with our arithmetic and we talk about two things you actually know very well already, presuming, but we have to say a couple of things, some things you might not, some tools you might not be aware of. And that is, first of all, primes, and then we talk about GCDs, greatest common divisors. So primes. Now, I hope that everybody knows what a prime is. So a prime P is a prime, it's a number, it's a positive number. Negative numbers are normally not considered prime if it has it cannot be factored. It's unfactorable. That's that's not an official definition, but we all understand what it is. It cannot be factored, unfactorable. Right? So like 17, there's no way to factor it. Well, you say, well, yes, professor, I can do 1 times 17, but that's not considered a real factor, right? And so that's the prime, and then N is called composite. That's perhaps a name that you might not remember or have seen. That's the opposite. That means not prime. And so an example here would be, for instance, 34, because that is 2 times 17. Okay, so that's exactly, we don't consider this a true factorization, but this is a true factorization in two smaller components, two smaller factors. Okay, we call these also divisors. So another way of saying that a number is prime, it's saying that it has only two positive divisors, 1 and 17. Or if you don't include the positive, it has 4 divisors, because don't forget the negatives are also divisors. Now, there's always a bit of the issue, what about 1? Well, 1 is kind of neither. It's kind of an outsider in this whole story. It's like a bit 0 is a bit an outsider, and 0 and 1 are kind of silly numbers we don't talk about. So I'm not going to say anything about it. It's not considered a prime, it's not considered composite. Okay. All right. So how do we find prime numbers? Are there prime numbers? Well, first of all, one of the oldest theorems that mathematicians like very much, because it's a very beautiful proof. This goes to Euclid. So Euclid proved there are infinitely many primes. That makes them interesting. Of course, if there would be only 7 primes, why would we talk about them, right? There's only 7 guys. We know, everybody would know them, or that's the end of it. But there are infinitely many. Now, I'm going to give you an argument for that, but I have to say a couple of things before I can do this. And so, the first question, and that we're now already addressed perhaps, is a very important problem. So, how to check that a number is prime? Well, that is not easy. Well, it is, I mean, there is a check, right? But the check is, you check basically, is it divisible by 2, is it divisible by 3, divisible by 4? But then perhaps you don't have to check divisible by 4, we'll talk about it a little bit, divisible by 5, so you check for factors, okay? So in other words, what you do is, so one way is try to factor. But that's not an easy problem to try to factor something, okay? And so how, because it's what you really have to do is check every divisor. And so this is time consuming. And that is what we're going to use in our cryptography, that it is very time consuming to factor a number. Okay, so if I give you a composite number, if I tell you in advance it's composite, but you have to find the factors, or at least find 2 factors of it, factor it, it's a very hard, it's time consuming. If the size of the number is big, and we are talking about numbers of size 100 digits, then this will take a lot of time, and that is what cryptography will exploit. Defining that something is checking that something is a prime, there are better techniques nowadays available, but I'm going to give you a couple of techniques, and one is a very old one, and so Euclid was a Greek from before Christ, so the first millennium BCE. Another one was Eratosthenes. So I'm going to go here to this guy, I'll make it a little bit bigger. So this is coming from Eratosthenes. I always have to see how exactly you write his name. There's a TH there. Eratosthenes. I already said it wrong. Eratosthenes. That's his name. And it's called the Sieve of Eratosthenes. And what is the Sieve of Eratosthenes? It's we're sieving out the primes. And how does it work? Well, let me explain it it is time consuming, but it gives you, at the end, when I run my sieve on this, the first 100 numbers, you will find all the primes in less than 100. Exactly will remain. So what you do is basically you throw out, you sieve out the numbers that are not prime. Well, the first one, so I'm going to do this in red, right? So red will mean that I'm done with them. No, sorry, I'll do this way. So 1 is not a prime, we know that. Now 2 is the first number that remains, so I'm going to take 2, and now I'm going to take steps. Every number that is step 2 from what I'm here, I'm going to cancel. So with 2, I'm now adding 2 to itself, that is 4, that I'm not consider this. Then add another 2, another 2, another 2. So you see what I'm picking out are what? The even numbers, right? So I'm deleting each of these, because are they prime? No, because they are divisible by 2. And there's another factor there. So by doing this process, I'm eliminating already all even numbers. But you see, it's kind of time consuming. I'll try to do a little bit fast here. Okay. Next thing, what is left? The smallest number that is left is 3. So that will be a prime number. And now I take every third. So I had 3 to itself, that is 6. Then I had 9. Oh, no, sorry, not green, red. I'm now gonna, so I keep 3, but then everything else, I keep adding it to itself, so-called arithmetic progression, right, of 3. So 3 plus 3 is 6, 6 plus 9 is 6 plus 3 is 9, 9 plus 3 is 12, so that's 15, 18, 21, 24, 27, 30. You see, some of them I'm cancelling twice, which I shouldn't do that, right? So I'm gonna skip those a little bit. 32, 36 I have already, 39 will go, 42 I have, 45 I have it not, 48 have cancelled out, 51, 54, 57, 60, 63. I'm always going by steps of 3. Well, I have that already, so let me not do that anymore. 69, 69, what is the next one? 72, 75, 78, at 3. Well, I'm just going to put it, because otherwise it's easier to just do it that way. Then you see also why. 1993, 96, and 99. So some are already out. I should not do them twice, but I'm just for the heck of it. Okay, I'm done. So what is left? The next number that is left is a prime, 5. And I do the same thing. I look at 5 and then add 5 to it, keep adding 5 to that thing. 5, 10, and I get what I get is exactly the powers of the multiples of 5, right? So for instance, 25 will be matched out, 30 will be out, 35, 40. It's very easy. The powers of 5 will be in these two columns, right? It's this column, and in this column I have already put everything is already gone, is already sieved out. So it's these guys that will now be sieved out. I hope you follow this, right? Okay, so the next one left, you see the primes coming, right? This is 7. And I do the same thing. 7, add 7 to itself, that is 14, 21, 28, 35, 42, 49. See, once in a while I blot something out. Not that often anymore, because the more I sieve out, the less remains, right? So then it's 56, I've lost track of time, 63, 70, 77, there's another one I'll get rid of, 84, 91, that's another one, and 98, I have that already. Okay, notice, I don't know whether you noticed this particular pattern of 7, it's not as regular anymore, the 5 pattern. In the 5 pattern it was just one column. In the 7 pattern, in the beginning, so let me repeat, right? This one, no, let me do it with the next one, 11. Although there's not going to be that many left anymore. Yeah, 11 perhaps. I should have pointed out, look at the video again and look, it's not predictable. It's not every 3 that I skip that I have to mark, because all the next 3 ones are already marked out. It's it's kind of, you cannot predict which will be blotted out. Okay, so the next one that remains is, this will go now extremely fast, 11. And so I have to now look at the multiples of 11. So 11 plus 11 is 22. So 22, 33, 44, 55, 66, 77, 88, 99. We all have already gotten rid of them. So 13, we look at 13. So we have to get rid of all the multiples of 13. That now, so 13 is a prime number, but everything else, so that would be 13, 26, 39, 52, 65, 20, 13. What am I doing? 13, right? Yeah. 78, 80, 91. Notice I'm not blotting anything out anymore. Okay? So what I'm actually claiming is all what is left now are already prime numbers. There are, of course, many more. Remember, there are infinitely many, but these are all the prime numbers below 100. And why is it that I know already that that I'm done with my sieving? Because there's another thing, that if n is composite, then it is divisible, then it has a prime factor I'm going to put the prime, it has a factor less than or equal square root of n. Why is that? Well, so if n is a times b, right? So this a and b are the factors, and I'm saying something about a. I'm saying a must be less than, so I'm going to do proof by contradiction. So suppose a and b are two factors, they're all bigger than radical n. Right? That is the negation. Remember, how does proof by contradiction go? You assume that we have a factorization, but you assume that, or you negate the conclusion. You assume the hypothesis, but say the conclusion is false. And that should lead to something silly, something that cannot be true. I'm saying that n is factored, but I am assuming that these factors are not less than radical n, so they are bigger than radical n. But well, let's see what happens if I multiply them. A times b is bigger than radical n times radical n, which is what? That's n, right? Radical n times radical n is n. And ab, well, by assumption that's n. Now I have here the silly statement, I'll put it in red because it's so silly, that n is bigger than n. And that is the contradiction. So that's the contradiction. So that's very quickly the proof that, so let me put a little box here saying I'm done with my proof, that there is a factor less than n. But what does this mean is, when we check that a number, so to check whether n is prime, we only need to rule out all divisors that are smaller or equal to radical n. So all these I can, because I know there has to be at least one. And if I ruled all those out, then there cannot be any. That means there is no divisor less than radical n, therefore it must be prime. Right? This is what it says. That's contrapositive, right? The contrapositive of this statement. So if then, the contrapositive is, if this is not, then this is not. If this is not the case, if there is no factor less than radical n, if I ruled out all the factors that are less than radical n, then this is not true. Then n is not composite, then n is prime. Prime and composite are a negation. Okay, so now what is the radical of 100 here? Remember, I was looking at all the numbers less than 100. So the radical of 100 is 10. So this meant I only had to check for primes less than 10 or equal to 10. So 1, 2, 3, 5, 7. Notice that when I looked at 11, I didn't rule out anything anymore, right? All these were already ruled out. And the same for 13, and the same for 17, 19, and so on. So in basically doing like going to the sieve 1, 2, 3, 4 times, I ruled out already all the other primes. And so that is speeds this process up. And so I conclude one more time. What I have found is that all the numbers that are left here are prime numbers. And you see how they are a little bit dispersed here. Sometimes you have 2 prime numbers. Here we have 3. Here we have 2 of the same. Start with here in the 90s there's only 1 prime number. And how the way the primes are scattered through the natural numbers is a pattern that we still do not understand. We have no grasp on that pattern. We cannot predict just how the pattern looks like. And the pattern is assumed to be very complicated and let's say, completely unpredictable, which people would call random. Although it's not random, we know it's a prime number. But this makes them so fascinating. It's not something, all the even numbers, we know what they look like. They all are end in 2, 4, 6, 8, and 10. But these guys, prime numbers is something that we have no grasp on how they look like. So one of the big theorems that we're going to use, it's called sometimes the fundamental theorem. So I'll call it, if other people, the fundamental theorem of arithmetic. Every number is a product of prime numbers, of primes, and basically in a unique way, well, up to, of course, since multiplication is commutative, we can put 2 times 7 is the same as 7 times 2. But I consider that the same factorization, right? In a unique way up to order of the factors. Let me not even say that. In a unique way. I'm just going to say that. And you understand what I mean with that. For instance, simple thing, let's take 40. 40 is 2 times 2 times 2 times 5. And here you see exactly the primes. Now, notice that some primes can occur several times. And the prime 3 doesn't occur, and the prime 5 occurs. And there's no other way that you can write this as a product of primes except for putting the 5 somewhere there, but that's the same factorization. So this is the factorization theorem that every number is a product of primes. And of course, a prime itself is a product of primes. It's one that we consider 7 is 7, that's a product of primes. It's a silly product because there's only one number, but it is, so it applies to primes too. But of course, what we really mean is that every composite number is a product of primes in a unique way. So, unique way. So the next question is, how do we find that? So finding the prime decomposition, we call this the prime decomposition. Prime decomposition of a number n. I'm going to do it on an example. Let's do the example. I'm going to take a rather big number so that you see that what is going on. What is going on here? Let me do 50, 40. Okay. So to do this by hand, if you want, and I want to emphasize, this is a difficult problem. I said this right. To find that a number is prime, or rather to factor a number, is time consuming. I said it, but let me write it down. It's time consuming. In other words, although it is still exponential, so it is still tractable, it's at least quadratic, I think, or something, or subquadratic, I forget exactly what it is. But it is, if we're dealing with huge numbers, it becomes too much work to do. And I'll talk about cryptography later, but just keep that in mind. It's time consuming. And so what we need to know for us, because we took smallish numbers, we need to know kind of the first. I hope everybody knows that these are the prime, the prime numbers less than 20 would be good to know that these two are. So okay. So what we do? Well, we here I'm going to list the prime factors. And I start with the smallest possible factor that I can do, 2. Okay, does 2 go in 540? Yes, it goes. So if I divide by it, I get 2520. Okay, so what I do, as I explained, I take this number divided by 2, and that's what I get here. So I'm doing the same. 2. Does 2 go in there? Yes, that will be, okay, let me do this here. I don't want to make mistakes. 2, 15, 20 divided by 2. That's 1260. 1260. So that is still divisible by 2. Okay, so let's do this. 1260 divided by 2, which is easier to do on the calculator. 630. Still divisible by 2. How do I know it's still divisible by 2? Remember, so here I'll put some notes here. Divisible by 2, let me write this a number, means ending is the same as ending in 0, 2, 4, 6, or 8. So it just from the digits I can read of it is divisible by 2. So okay, see, because it ends in 0, I know it can be divided by 2. So I do it one more time. That's 315. 315, so 2. Is it divisible by 2? No, because 315 ends in 5. So no. Okay, so next question, I look at the next prime, 3. That's the next prime. Is 315 divisible by 3? The answer is yes. How do I know that? So let me put that here. Divisible by 3. Of course, I can check it with my calculator, right? But I can see it. It's not so hard. If the sum of the digits is divisible by 3. So if you're divisible by 3, then also the sum of your digits is divisible by 3. So what is the sum of the digits? 3 plus 1 plus 5. So 9. That's divisible by 3. So you reduce the bigger number to much smaller number, the sum of its digits. And you can repeat that process, right? If the sum of the digits is still a number that is 3 digits long, well, do it again. Keep doing it until you see a number that you recognize as a multiple of 3. So yes, it's divisible by 3, so I can divide by 3 here. And that is 105. So I get 105. So the next number, I know 2 is not going to be there anymore. We have done with 2, so I keep now looking at 3. Okay, is this number divisible by 3? Remember what I said on the right hand side here. The answer should be therefore yes, because the sum of the digits is 6. So if I divide this by 3, I get 35. So this is divisible by 3. Is this divisible by 3? The sum of digits is 8, so no. I go to the next, not the next number, not 4. That cannot be anymore. We go to 5, the next prime number. So is 5, is it divisible by 5? And the answer is yes. How do I know that? Well, I'm sure you know this one. When is a number divisible by 5? Is if it ends in 0 or 5. Exactly in this case. So it ends in 5, so yes. So we divide by 5 and we find 7. Of course, this 7 is a prime number, but let's see what would we do. We look at 5. Is 7 divisible by 5? No, because it doesn't end in 5 or 0. So I look at the next prime number with 7. Is 7 divisible in 7? Yes, and the result, of course, is 1. Once I read 1 here, that means this, what I found here, is the prime decomposition. So we have 1, 2, 3, 4. So we have 5040 is equal to 2 to the 4th. 4 times the prime 2 occurs, the prime 3 occurs twice, and the other 2 occur just once. Okay, that's the technique. I let you practice this, so I don't want to say too much more about it. So now the next thing, I want to go to this Euclid's theorem here. There are infinitely many primes, and so I want to give the proof that Euclid also did. Assume, and this is again by contradiction. So you might think, oh, contradiction, that is a very fancy thing, that must be like something they invented like 3 days ago or three years ago. No, this is as old as the Greek mathematicians, and also not only the Greek did this, but Euclid was the first to actually write it down. So assume not. So that means, what does that mean? So assume that there are not infinitely many primes. That means that P1, P2, I'm going to P of prime, right? I'm going to just enumerate all them. P, I don't know how much, so I'm going to say Pm are all the primes. No, there are only finitely many, so I can list them. P1, P2, P3, up to Pm. Pm. There are m primes. Say 7,300,422 primes, and that's them. And I list them all. And then now look at the number n. I take P1, multiply it with 2, P3, so I multiply all these numbers, so multiply, not add. So I'm multiplying all together, Pm, and then, that's what you do, right? If kids say, I want to make a big number, and then one says a million, and another says a million plus one, and then says billion and trillion, and then one says, very smart guy says infinity, and the other says infinity plus one. So that's what we're going to do, plus one. Make it just a little bit bigger. But now, we know the prime factorization. So this is something that we need to know before this, before we can make that proof. And Euclid, again, gave an argument for this, although this is a bit more difficult to prove, but it is something that we all accept. Okay? This is something that we know how to do and check. This other thing, there are infinitely many primes. How are we going to check that there are infinitely many primes? We can run a computer, but if there are infinitely many, it will never stop, right? Because you keep finding new ones. So that's the problem, right? So what do we say? What we use this now? We say this number here, this, let me call it Q instead of M, because otherwise you guys say, well, this is an M, professor, and you already used an M. No, there was an N anyway, but anyway, let me call it Q. Now we know that Q can be factored in primes. So some prime must divide Q. In other words, if I do my procedure that I had here, I start with the smallest. Let's say that we listed them in order here, right? Let's make that that's not necessary, but let's assume. So I first check whether it's divisible by P1, and then keep scratching out P1, and so on and so on. So some prime must divide Q, but they're only finitely many, so it must be one of those. So say, okay, I need a little bit space here, so I'm gonna erase this thing. P7, some prime, but to be really correct in the proof, I should say Pj, because I cannot say 7. But just for sake of the argument, assume it's P7. If that's P7, let's see, so P7 divides Q. What about this number? Is this divisible by P7? Yes. So can I write P7 divisible by Q? I can use my fancy notation. Sorry. That's not. I'm not using my fancy notation correctly. Sorry. Let me say, P7 divides Q. This Q, not 9, right? Oh, I hope that you don't object to that. That's Q. P7 divides Q means that Q is equivalent to 0 mod P7. It's a fancy way of saying it, but sometimes make it much easier to think about it. Q is equivalent. Now P7 will also divide this number because it's one of the factors, right? It's the 7th factor. So P7, so let's look at this as not an equality, but an equality mod P7. Okay, what we have? Well, I just found that this is 0, so this is 0. Okay, I also found that this thing is 0, so this is 0. So what I'm left with is 0 is equivalent to 0 plus 1. Don't forget there's this extra plus 1, right? That was the infinity plus 1 that we were trying to do. Mod P7. What does this mean? That means that 1 is equivalent to 0 mod P7. This means that P7 divides 1. P7 divides 1. But that's impossible. Here we go with our it's impossible. That's a contradiction. Because no number divides 1. That's why we ruled out 1, right? It has no divisors. It cannot be factored. Well, 1 times 1, but that's not a factorization, right? Okay. So that's the proof that Euclid gave. It's a proof by contradiction. Now, then other problems come with, okay, there are infinitely many primes, but how are they spread out? And I'm going to say some things, I'm not even going to write it down, you can read it in the textbook. One of the things that they have proven later on is not only that there are infinitely many primes, but in every arithmetic progression. So an arithmetic progression is one of these that we done in the Sieve of Eratosthenes, but not necessarily starting with a number. So, for instance, arithmetic progression if I start, let me do it in purple, start with 25 and let's add 6 to it. So that would be 31, 37, 43, 49, 50, I should not have circled it. Let me undo the circling and let me, undo the thing and let me circle it, sorry. So I'm starting with 26, no, 25 and I added 6, right? Okay, let me do it that way. Sorry, 25 and I'm adding 6. And the one thing I need is that the greatest common divisor between 25 and 6 should be 1. We'll talk about greatest common divisor in the next video. So, what do we have here? 25, and I'm going to start adding 6. So the next one will be 31, then 37, then 43. You say, oh, they're all primes, but not always. 49, the next one is 55, the next one is 61. Another prime. 73. Oh, I'm picking up a lot of primes. Look at me. I didn't know that I must admit, I'm a little bit surprised how many that I'm picking up. But still, 91 is not 1, 97 is 1. So sometimes I pick one up, sometimes I don't. And the whole deal is, and that is, again, not only are there infinitely many primes, in other words, if I keep doing the Sieve of Eratosthenes, not just on up to 100, but up to basically all numbers, which I don't know how to do that, but if we could do that, there would be infinitely many green spots. But what I'm saying is, if you look at the arithmetic progression, like the purple one, there will be also infinitely many of those will be green. There will also be prime numbers. Okay. There's then a famous theorem also that I will quickly as I said, I'm not going to do everything that the book does. The question is then, if there are infinitely many primes, how many are there then? Can we somehow measure the number of primes? So then let's calculate the number. P is a prime. So we look at the set of primes that are at most x. So for instance, here x could be a 100 in our sieve. Let's see then if x is 100. So let's call this the so let's call this, I'm going to give it a name. Let's call this number, prim x. So prim x is the number of primes less than x or equal to. So what is prim of 100? So it's a function, right? Well, it's a counting function, and really it is. I cannot say too much about it. I can only count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 3, 4, 5, 25. I hope I didn't miscount, whatever, 25. So this function, now there's a theorem due to Gauss, and this is a very important mathematician. Euclid was a very well, I've heard perhaps of Euclid. You have probably also heard of Gauss, the Gauss curve. He was one of the first modern mathematicians. He's sometimes called the Prince of Mathematics because he did so many things. And he proved that the prim x is a bit the same, almost, in the order of magnitude, if you want, as x over ln x. Okay? So, in this particular thing, and the log here is the natural log, right? So the natural log of 100, let's see what this would be. 100 natural log, where's my natural log? Log 2, log 10. I don't have natural log on my, log e, okay. It's 4.6. So if x is 100, then the ln of x is 4.6. So this number for x is 100 is 100 divided by 4.6 is about 21. Now we calculated that this was actually 25. So it is not equal, but the amazing thing is, because this is a very small sample, and for those that have ever seen statistics know that to get statistical behavior, this is a statistical behavior by the way. So here I'm saying statistically, this function is almost the same as this function. So in average, if you take a big X and you count the number of primes below X, or you count this value, it's going to be two numbers that are very close to each other. for whatever axis you take. Okay, 25 and 21 in the same magnitude, but you cannot check this here on this small sample size. Okay, so that's that's that. Now there also primes are fascinating for mathematicians and also have fascinated mathematicians and human beings in general for centuries because of their erratic nature, right? They are unpredictable. There's still very many of them we don't know, and there's a lot of things we don't know. So, for instance, the following question. Look at this. Okay, let me highlight a particular pattern here. So I'm looking at these primes here that are two apart. So these are called twins. You see, there's once in a while I find a twin. This is a twin pair, but not that many. Okay, so I have 1, 2, 3, 4, 5, 6 twins that I found less than 100. But that you say that must be probably not, right? And in fact, if you look at this growth rate here, think of this growth rate, it's kind of unlikely that there are going to be a lot of twins. But for some miraculous reason, we have now calculated primes up to 10,000, 100,000. They have tables of those things. We know exactly all the primes up to a certain, I forget now what it is, and every day I'm sure the pound expands. One sees constantly, once in a while, these twins appear. So we don't know whether there are infinitely many twins. That's a conjecture that we still don't know. So open problems. So if you ever want to become very famous mathematician, if your notion of fame includes this kind of stuff, then show that there are infinitely many twin primes. We have no idea. Okay, and there's a lot of work on that, and at the moment we have a couple of we have checked it, by the way. The biggest twin prime that they have found so far this is in 2011 according to the textbook. I'm sure it's bigger. I didn't Google it. It has about 100,000 decimals. These are huge primes, right? And even there you find still twin primes of that size. Okay. So just to tell you, I want to give you perhaps an example of a twin prime that is a bit bigger than the ones that we saw, because you might think, oh, this is just because we have only two decimals. Here is one, 4967 and 4969. Now you might think, well, how do I know they are prime? Well, no, you don't. You have to check that. But if you check those, they are both prime, then they are two apart, so they are twins. Okay. So another open problem is what is called the Goldbach problem, or Goldbach. The fancy word that mathematicians say is conjecture. They conjecture this. The Goldbach conjecture says that every even integer is a sum of two primes. Okay, so for instance, 8 is 5 plus 3, right? And 10. Not 5 plus 5, yes. I didn't say that it has to be different, right? There's another one, 7 plus 3. 12. You have to think a little bit about, right? So it's not obvious 7 plus 5, okay. 14, 7 plus 7. 16. Anybody sees this? 11 plus 5. And so it's not obvious to predict what the two primes are going to be. And so, as of to date, we have checked this, that every integer less than, so true for all n less than 10 to the, where is it, 10 to the 18. This is again 10 years ago, basically. The textbook is a little bit older here, using an older version. So it is probably better now, but so using conjectures, we have proved this for every even n that has 18 digits or less. We can find two primes of which that add up to that number. Quite remarkable. And there's a variant of that. It's a bit annoying that we have an even integer there. In fact, the original problem said something else, said that every odd integer is a sum of 3 primes. You can also check that. And then Goldbach actually figured out that actually that's the same as saying that every even integer is a sum of 2 primes. I don't exactly remember how the argument works, but these two are the same. So in other words, if you put them both together, this every integer is a sum of either 2 or 3 primes. Even that we don't know, okay? And there are many more. I don't want to say too much more about those. Other conjectures, read a little bit more in the textbook. Now, this concludes the lecture on primes, but I want to also include a lecture on the GCDs, creating common divisors, and that I will do in a separate video so that I don't make the videos too long.